In this example, we'll solve a simple problem of a one-unit non-reactive mass balance. So obviously, whenever you get a question, first thing to do is read through it once. So we'll quickly read through this. 500 kilograms an hour of a mixture containing 70% component A and 30% component B by mass are fed into a separator that operates at steady state. The top product stream contains only A, while the bottom stream contains 20% A by mass. Calculate the flow rates of the two products. So when I read this question, first I'm going to go through and mark some important things that I noticed. So I'm told 500 kilograms of a mixture is fed into a separator, so I know what my feed is. I know that it contains 70% A and 30% B by mass, which is important, because that could be by moles, by volume, I don't know. Now, they also tell me that it operates at steady state. We know that the top product stream contains only A, and the bottom stream contains 20% A by mass. So now we've gone through, we've read, we've marked a little bit of the details. The next thing to do is to draw a diagram of the process. So we've got some separator. And we have a feed into the separator, and we're told that it's 500 kilograms an hour of a mixture that has 70%, so 0.7 kilograms A per kilogram. It's another way to write 70% A by mass. And we have 0.3 kilograms B per kilogram, right? So that's that first line. We're told it operates at steady state. We have a top product stream and a bottom product stream. We'll draw them out. We know that the top one contains only A, so we'll write pure A under this. And we know that the bottom stream contains 20% A, so by mass. So this is going to be 0.2 kilograms A per kilogram. That's all we've been given to draw. Now we need to fill in some of the blanks. Now we're going to mark what we don't know with letters as unknowns. So I'm going to mark the top stream as M1, and it's going to have units of kilograms per hour. I'm going to mark the bottom stream M2. That's also going to have units of kilograms per hour. And another thing that I wasn't told, but I can infer from the data, I'm told that this stream contains 20% A by mass. And since I know that I've only had A and B coming into the system, then we can fill in the blanks and say that it contains 80% B by mass. Okay, so we mark down everything that we know. Now, the next thing to do is to select a basis for the problem. Now, in a case like this, we've already had the basis selected for us. We've been told that we have a feed of 500 kilograms per hour, so this is going to be our basis. But you may encounter questions where you're given data in a way where you have to select the basis. And when you come to that kind of situation, you're going to want to select a basis that's going to make your life easy. So usually you want numbers like 100, 1,000, 10, things that are nice and round numbers. And the second thing is, what if, for example, I wasn't told how much feed I have, but I was told that I have the 70% A and B by mass, then I'd want to select 100 kilograms per hour because I'm told the mass fraction. I wouldn't want to select 100 moles per hour, for example, or 100 liters per hour, because that would just add conversions that would make my life more difficult. So try to pick a basis that makes your life easy. Now, the next step we're going to do is we're going to draw a little table, and in that table, we're going to write what balances we can do and what unknowns each balance has. So we talked previously about mass balances, and we know that we can do balances on each of the species that we have in the system, but we can also do a balance on the total flows in the system. So in this case, I'm going to write out, first of all, the total mass balance, which is, what comes in must come out. And then we have balance on component A that we can do. and a balance on component B that we can do, meaning A that comes in must come out, and B that comes in must come out. Now we want to find out what the unknowns are. So first of all, we circle our system. In this case, the whole separator is our system. And when we look for the unknowns, we look at the flows going in and the flows going out, right? So in the feed flow, everything is known in the total balance, right? 500 kilograms per hour. For the total balance, we're only going to be looking at the flows here. So M1 and M2 are unknowns, right? Now we go to component A. In the feed, we know everything about A. In the top stream, we know that it's pure A, but we don't know how much of it. So M1 is going to be an unknown because we have to multiply M1 by 100% to get the amount of A. And then in the bottom stream, we know the mass percentage, but we don't know of how much that is. So we'll have another unknown here, which is M2. Finally, when we do the mass balance for B, we know everything there is to know in the feed, right? 0.3 times 500. There's nothing in the top stream for B, so M1 is not an unknown for B. And when we go to the bottom, we have 0.8, but we don't know 0.8 of what, so M2 is an unknown. Okay, now that we've drawn this out, we can kind of map out how we're going to solve the problem. So again, we're going back to our degree of freedom analysis, right? In terms of the degree of freedom, we have the number of unknowns minus the number of independent equations minus the number of other equations. So now let's look at our table and we'll calculate the number of unknowns for each balance. So the total balance, that's one balance, that's one independent equation. And the number of unknowns, we have two unknowns. So 2 minus 1 equals 1, right? So solving this balance is not going to give me both M1 and M2. For A, we have the same case. We have two unknowns, M1 and M2, and we just have A. So that'll give us, again, we can't solve the whole problem just by doing a balance on A. On B, we have one independent equation and one unknown. So in that case, we'll be able to solve that equation, and that'll give us M2. So when you're doing this degree of freedom analysis, you're looking for the simplest way to start. You want to map out. The question asks us to calculate the flow rates of the two products, which are M1 and M2. So we have to solve all of these. But if I was told to just solve for the bottom product, then I would only do a balance on B, and I'd have the solution already. But since I need to solve both of them, I'm going to do a balance on B. Once I solve the balance on B, I'll know M2, and then when I go to do a degree of freedom analysis on either A or the total, there'll be just one unknown for one equation, and I'll be able to solve for M1. Now, obviously, you can just take the total balance and the balance on A and solve them simultaneously in a system of equations, and you'll get the solution to both of them. But the idea here is to simplify your life and only try to solve one balance at a time to get a piece of information that you need. As the problems get more complex, you'll find that you can really ignore a lot of the systems, ignore a lot of the balances, and really find a very smooth and elegant way to get to the solution you need. So now we've mapped out our route to solve the problem, which is we're going to do a balance on B, which is going to give us M2, and then we'll do a total balance, which will give us M1. And obviously you can do a balance on A, but typically the total balance is simpler than a balance on A, because if you do a balance on A, you have to multiply M2, for example, by 0.2, whereas if you do the total balance, you just take M2. All right, so let's start with a balance on B. So I'm going to write out the mass balance, which is A equals I minus O plus G minus C. Now again, we were told that this is at steady state, so accumulation equals 0. And it's a non-reactive system, so G and C both equal 0. And the balance ends up being in equals out. So now we look at our system, and we go first in. What goes in? For B, we have 500 kilograms per hour multiplied by 0.3 kilograms B per kilogram. And that'll give us how many kilograms B per hour we have coming in. And going out, there's nothing in the top stream, so we ignore it. And in the bottom stream, we have M2 kilograms per hour times 0.8 kilograms B per kilogram. And you solve this, it ends up that M2 equals 187.5 kilograms per hour. All right, so we solve for M2. Now we can choose either one of these balances. I said before I'm going to do the total balance. Okay, again, I'm going to write it out. And this is just a good habit to get into, to write out the balance and take off whatever you don't need, just so you never miss anything. So again, there's no accumulation because of steady state, non-reactive system, both of these equal 0. So again, in equals out. Now we're looking at the total balance, so the in is 500 kilograms per hour. And that's going to equal M1 in the top stream plus M2 in the bottom stream. And we just solve for M2, so we can plug that in. This is 187.5, and we get that M1 equals 312.5 kilograms per hour. So we solved for M1 and M2, the product streams. And again, you can go back and do a mass balance on A and convince yourself that you get the exact same answer. Hey guys, hope you enjoyed this video. If you did, please subscribe and turn on notifications for the next videos. If you have any questions, leave them in the comments and I'll do my best to answer them. And I'll see you all in the next video.